Hello everyone, in today's video I'm going to make a video about the small little blinking lights that typically draws around 80 to 90 microamps at around 230 volts AC to light up some LEDs. The reason behind making these lights is that in case of indicators, you don't actually need a continuous light. A blinking light will work. On the other hand, a neon bulb can draw around 150 microamp to 200 microamp, which is double the current that these lights consume. Now, when it comes to AC, the neon bulbs can actually outperform LEDs. The LEDs will require some forward voltage. In case of the neon bulbs, they also need a higher voltage, but the current consumption is very low for the neon bulbs. You can literally make the voltage so low, the neon bulb can still draw around, let's say, 50 microamp or something like that, and will still give you off light. In our case, this still holds true, but because we have blinking lights with lower voltages, it will take more time to get a capacitor charged so the light can glow. It will still blink at lower voltages and even at higher voltages, but the blink rate can differ. This kind also gives us clear indication about the voltage as well. So these lights will start glowing at around 65 volts. I have tested with my auto transformer, and it will glow up to 600, 700 volts or something like that. I have also tested that. And the thing is that this can glow up to few kilovolts in fact. But due to the limitations of the PCB, like the clearance and the creepage distances, it might not be that practical, right? I cannot really have a gap in this small little PCB. So this is around 0.75 to 1.5 mm of creepage distance and clearance as well. So this should be perfect up to, let's say, 400 volts peak I have calculated. So yeah, if you give it more volt, that might be okay. I have also tested this at around 600 volts or so. They work perfectly well, but they do have two resistors, SMD resistors in series, so they can take up to 800 volts for 100 milliseconds. So that's the limitation, but in reality I have checked that you can give them 600 volts happily and they will run for more than few hours. That's not a problem, but in case of high humid condition or something like that, of course you don't want to run them at that voltage because the traces might short out or something like that. So anyway, let's see how this circuit works. I have actually made this circuit in a breadboard. You can see that it's a tiny little breadboard. Let's jump onto an EZDA schematic and see how this thing actually works. So the schematic is essentially this, but in the original circuit we have a couple of that connected in this configuration. So this is one part of the circuit and this is the other part of the circuit connected in series. So they together consume around 90 microamp. But in our original circuit we have a couple of inputs, of course, and we have three 1 megohm resistor that connects to a full wave bridge rectifier. Through this diode it charges up this capacitor here, and the capacitor, when charges up, has nowhere to go except this DB3 diode. So whenever it charges up to 28 to 32 or maybe 34 volts or something like that, the DB3 diode will reach its breakdown and will charge up this capacitor. Now we have a zener here to make sure that we don't overvolt the LED, and we have three LEDs in parallel. We can connect them in series as well as the voltage is high. In this case, most of the energy will be stored in the inductor and will get smoothed out. And if you don't have the inductor, the lights will still blink, but it will not be that good. So we can connect another diode in the inductor, but the issue with that is that I have actually seen no benefit. So if we connect a diode, that might make it a little bit more efficient, but if you see no change in the light, of course, why would you, right? The main purpose of that circuit is to fit in the indicator lights, and they have to be very small. So if we have another diode here, that might make it a little bit bigger. So if you take a look at the PCB I have designed, you can see that it is quite compact, right? So this is the 3D view, and here we have a couple of 1 meg resistors. So here's one and here's the other one, and it is connected in series, and we have three LEDs that will glow independently. So these two pairs, this one and this one, will glow together, and this one glows independently through the 4.7 microfarad capacitor. So this is the overall circuit here, the actual circuit that I have shown. It is very simple circuit and kind of work really nicely, because even if you overvolt them, or maybe you have surges in your lines, or even if you have under voltage, the indicators will still work. So in the next upcoming video, I'm going to show you an earth detection circuit that you can detect earth with, right? So basically that will consume around 50 to 60 microamp or something like that maximum. My target was even less, so that it can detect earth without triggering GFCI or potentially giving any tingling sensation. So basically the idea is that instead of the LED, you can have an optocoupler, and the optocoupler will light up at around 1.2 to 1.5 volts. And the other side of the optocoupler will be connected to a retriggerable monostable multivibrator IC like this one, which is SN74123N. And if you connect this IC there, it will detect the pulses and will detect the earth. So you can detect the earthing at around, let's say, 30-40 microamps or maybe 50 microamps, which is less than what a tester draws. So that is perfectly safe for human body, even though you will feel a little bit of tingling if your hands are really dry. Yeah, I mean 50 microamps will still give you some tingling sensation. So yeah, this is very basic circuit. Let's hop onto the testing. So basically we have the full wave bridge rectifier here, and we have a couple of 2.2 mega ohm resistors here. So what happens is that when the AC comes through that, it gets rectified into DC, and through a diode it charges up this capacitor, and we have a dB3 diode here. So whenever this reaches up to 28 to 32 volts, there's the diode that will reach its breakdown voltage. It will charge up this capacitor. Again, this is to smooth out the peak voltages. This will store that voltage and slowly release that to the LED. Now we have an inductor here, and this inductor makes the light way brighter actually. So this kind of works like a buck converter, but it is not really. So when you connect a scope there, you can see that the inductor kind of smooths out the duration that the light can blink, and this will light the LED longer. Now this is a 680 microhenry inductor. It could be a 1 millihenry or maybe 10 millihenry. Now note that if you have higher inductance and the core isn't that good, in that case of course there will be more turns, and that means there will be more resistive losses, right? You want to balance out that thing, so you want to choose a core and the winding that shouldn't really make the light dimmer. So in our case these inductors work. I have also tried with a 1 millihenry resistor looking inductors. So those are called axial inductors, and I've tried with those axial inductors and they work perfectly well. So let's actually put this thing into practice and see how it works. We are going to see everything in the oscilloscope here. So actually this is the PCB that I have made. Let me focus the camera a little bit so that you can see better. So you can see that we have 3 LEDs, and this one LED will blink first and then the couple of LEDs will blink later. So we have completely different circuits. We have 2 full wave bridge rectifier, and we have 3 LEDs that will blink independent to each other, which will give a nice little effect. And we have 2 inductors. Like everything is duplicated from this circuit, right? And it fits perfectly inside this indicator. So yeah, this is a very fun little project, and of course this is kind of electricity saver because indicators are essential for our house. So anyway, let's connect this to the 220 volts source. It is actually 230 volts AC, 50 Hz in India right now. Yep, let's connect that. So if I turn this on, you can see that there's some glow in here, and this is not really bad, but it glows really nicely actually. So is this thing safe to touch? Yeah, the other part is quite safe to touch. And to be honest, let's measure which is the live. Probably that is the live. Yep. Let's disconnect the circuit. This is the neutral one, right? And I'm going to actually touch that to see if that glows. It should glow because we have a 2.2 mega ohm resistor here, and we have a 2.2 ohm another resistor. So if I touch that, I shouldn't get any shock and the light should glow. So this kind of works like a tester as well. And my feet is on the floor. Let me touch something that has direct earth, and you can see on the scope as well that it glows. Now if I lift my feet up, you can see that the blink rate has reduced. It blinks, but the rate has reduced. So let me change the horizontal time base of the scope to something like 100 millisecond. There's a little bit of noise here, as I can see, but that's okay. We are set to 1 volt. Change the scale to, let's say, 5 volts. And you can see that there's a little bit of spike. This is quite interesting. And the whole point of this light is to have something that glows at around 100 microamps or less. So if I turn the source off and connect through this capacitor in here, so we can see what's going on across the cap. It is like an RC circuit. If I change the voltage to, let's say, 10 volts, you can see that this kind of thing is going on. We have around 34 volts. So the breakdown is happening at 34 volts. And whenever that happens, we are going down to something like 20 volts because we have 10.4 volts here. So we are getting around 20 volts when the holding current of the diode is less. So it cannot conduct anymore. The LED stops glowing. So this is the thing that happens, and it kind of draws less than a tester. You can see currently this circuit with couple of 2.2 mega ohm resistor, which is 4.4 mega ohm resistor, you can see that it draws around 60 microamp. And for the circuits that I have here, they have actually a couple of 1 mega ohm resistor here to make sure that we are rated over the resistor's voltage. I cannot use one here because our voltage is around 250 volts AC, and that is 350 volts peak. We want to make sure that we are not stressing out the resistors, which can fail over time or can reach breakdown if something nasty happens. That is it. I hope you enjoyed this video. Please don't forget to hit that like button and also press the subscribe button. Again, thank you for watching and have a great rest of your day.